Hello, welcome to this webinar. The focus of this is water vapor transmission rates and insights into testing these high barrier encapsulation materials and really looking at kind of the unique diffusion pathways of these materials. I'm Joel Fischer. I'm a scientist and laboratory manager here at MOCON. For permeation testing, I just want to review what it is that we're measuring and how we measure it and some key consideration factors that are really important when we start looking at encapsulation materials. First of all, if we ask about what is permeation, what we're looking at how gases move through materials, and we look at it through a three-step process. What we have here in this diagram shows that there can be gases here on one side, a very high concentration of those gases, and a low concentration on the other. We have this barrier material or the encapsulation material in between. And what permeation is, these molecules will absorb into the surface of the structure, diffuse through it, and come out on the other side. So it's a three-step process of the absorption, diffusion, and desorption out the other side. That occurs in nature with oxygen, water vapor, CO2, any kind of gas that's in play here. And it's just a physical property because gases don't like to be contained. Things want to come to equilibrium. So if you have a humidified environment and a dry environment, that humidity wants to come through and come into the dry environment. Some takeaways of this is when we look at the permeation or transmission rate, when this flux coming through, is the area of exposure. If we have a very large area, we can have more molecules permeating through. And we have a very small area, which happens a lot with the kind of encapsulations, we'll have low amounts of water vapor coming through. So the area of exposure becomes very important to the measurement when we're looking at water vapor moving through materials. Another thing we look at is Fick's law. So there's physics behind here of what drives permeation. In this case, we work with a high concentration on one side of the film and a low concentration on the other. In the case of water vapor, we're looking at humidity. If I use 100% RH as my test gas and a dry nitrogen gas over here, that provides a very large driving force or a gradient across the material. If I use like half the amount of humidity, like 50% RH, this driving force is going to be lower and the flux coming through it is going to be less. So when we look at this flux coming through the material, the water vapor coming through it, it's going to be dependent upon this concentration gradient. The higher the humidity, it gives us a higher concentration gradient and a larger signal. And also the innate diffusion coefficient, how fast do these molecules wiggle through. Another factor is the thickness of the material. When you double material's thickness, the transmission rate will cut in half, so less water comes through. An artifact of that is, yes, you reduce the transmission rate, but also it takes 4 times longer to reach equilibrium. So a test that may be kind of quick for one sample, here's an example of a graph of transmission rate versus time, will be slower if I'm using a much thicker material. It'll be 4 times slower. This uptake curve will be much slower. So some takeaways of this is that the concentration gradient does impact the transmission rate. The higher the concentration, the higher the net transmission rate that's coming through. So that's something to consider when we're testing these materials. And also, the thickness of the sample impacts also the transmission rate. The thicker the sample, the lower the transmission rate of water coming through it. I think that's important to see because a lot of the materials that you're testing when you deal with electronics and encapsulations are very high barrier materials. I talked about this graph here where you have like a low barrier sample. You can challenge it with humidity. It's going to come up and be very quick. You can have something that's a very high barrier sample. High barrier means low transmission. And we might not actually see much come through. In fact, when we had the sample, this let's say be a film here with, let's say, aluminum foil, maybe a polyethylene sealant. Because this comes from atmosphere, there's going to be some absorbed water within the sample. When we put it on to test it, we may just see the outgassing of the absorbed water and really nothing breaking through or coming through this high barrier aluminum or a high barrier coating like a silicon oxide or the like. So another takeaway is like, boy, the higher the barrier the sample is, the longer it can take to actually conduct a transmission rate test. Yeah, for this slide here, we're going to look at temperature and how it really impacts the transmission rates that we're measuring. So if we look at the top left diagram, That's a familiar diagram where we have all these molecules on one side of material. We've got the material in the middle, and then we've got smaller quantity of those same gases on the other side. And for permeation, gases don't want to be contained; they want to diffuse through. So we've kind of talked about that. But the speed of which they move through, that diffusion coefficient, is really tied to temperature. Temperature is energy, and with more energy in the system, the faster those molecules diffuse, the faster they wiggle. They just move quicker. So with increasing temperatures, I've got increasing energy, I have a higher diffusion coefficient, and then more water vapor transmits through my encapsulation material. Kind of to show you the impact of transmission rate versus temperature, it's our graph in the upper right. What you see here is a film. This happens to be an oxygen transmission rate test, but it was analyzed with 100% oxygen at various temperatures. We started out near ambient, near 20C. You go through 40, 60, 80, and you can see that, yes, as temperature increases, the transmission rate increases. Above 80C, it continues to increase. The general rule of thumb is that for every 10C increase, transmission rates double. And so you see this increase, and things really take off, at very high temperatures. What we do have here, though, is I've got a section that I've got like more of the moderate temperature, the blue area, and then the very high temperature testing, which is the orange area. And the reason why we segregated those is there's one thing that can be done with these permeation tests. It's kind of neat, and it allows for like predictive calculations of transmission rates at other temperatures, at various temperatures. And that's to do something called an Arrhenius plot. So in the lower left, what we've done is we've taken that data of the temperature versus transmission rate, but we processed it a little differently. For the x-axis, we've got 1 over the temperature in degrees Kelvin, so we've got the absolute temperature there. And then for the transmission rate, it took the natural log of the transmission rate. And what we see, what's kind of neat, is a straight line out of it. At least the blue area is very straight, very high correlation to it, which is really nice. In the orange area, that's still straight too, but you can see a little deflection point right really near this 8590C. So what's going on there is the material is changing, given the fact that this high temperature is now doing something to it. And the most common thing for the material to undergo is something called a glass transition point, where it becomes maybe more, it changes form, changes a little bit. Maybe it's more plastic or elastic now under this very high temperature condition. And these are, high temperatures. So what's going on there is the material's changing, and if the material changes, then how the molecules diffuse through it will change too, and it really takes off. So one of the things I want to point out there is that this using high temperatures is a great strategy to measure transmission rate for materials that are high barriers. But if you take them above the glass transition point, I think you can have some good comparative data. But if you're trying to do things that are predictive to understand what's going to go on at lower temperatures, it may not work as well for you as you think it is. So definitely something to think about, because if you're accelerating the testing, trying to get results out of it, you don't want to be like damaging or harming the material or taking it into a phase that maybe it wouldn't really get to in real life. So that's a strategy that's often utilized. Also, something to kind of show off is what high temp testing does is it makes the test faster. It gives us these higher transmission rates I talked about, but with those molecules moving faster, the time to equilibrium is also much faster as well. Example here in the lower right is a graph of a material that's tested for its water vapor transmission rate at 85C, then 50C, then 23C. And at 85C, we can actually see that within about 24 hours, it comes up to a nice equilibrium level, and it stays constant over another 24 hours. So that's very nice, very flat, and we accelerated the water vapor through it. And then what we did is we turned the temperature down. So we already had that gradient set. We had the molecules, challenging one side, moving its way through, being soluble within the polymer. And then when we turn the temperature down, what we see something is pretty neat is that we get a pretty good response. Like as soon as the temperature cools down, those molecules slow down within the sample, and then you'll see the transmission rate drop, and pretty quickly too. So that has actually shown like, hey, within 24 hours after dropping from 85 to 50C, we're at a very stable level, and we ran it longer just to prove it that it wasn't changing. And then after that was stabilized, that we dropped it again from 50C to 23C, and it took a little bit. It still dropped relatively quickly within 48 hours. We had a nice, good, stable value at 23C. So one thing I want to point out is that sometimes, many times actually, when we're dealing with encapsulations, with these high barrier materials, maybe long pathways and things like that, it can take a long time to reach equilibrium, but using the strategy, a higher temperature can help set that gradient faster and can help reduce maybe the overall test duration. So within this point here, let's say within 200 hours, we have data at 85C, 50C, and 23C. So very efficiently, we're able to process through the testing. But if we were only going to test at 50C, it could have took actually much longer than the 100 hours than we see here, just because things are coming through. Or at 23C, it could have been a very, very long test all by itself. So the strategy of using high temperatures and maybe even multiple temperature points is actually it's pretty unique, but it's so to do with an everyday permeation testing, but within electronics and these high barrier samples, it is really a common or a neat tool to utilize. The only caution here is kind of like beware of glass transitions or materials that might change, that you don't take them too high when you're setting that gradient, that you might be changing the material. So let's talk about permeation testing. How do we do it? How do we handle it? A typical test that's done is on a flat film structure. It's a barrier material. So what we saw on that first diagram, with all these molecules on one side, a barrier material, and the low concentration on the other side, we're going to really mimic here when we set up a sample. So typically what we'll have is a material that's roughly 4 by 4 inch square. We mount on top of this diffusion cell cartridge. This other cartridge clamps in place, so kind of like goes on top of it, and it sandwiches the material in between. So what we can do down here on the bottom side is we can put a controlled humidity, 90% RH, 75% RH, or we could even put a little wet sponge down here. On the other side of the material, when this is all clamped together, we'll have dry gas sweeping here. If I look at this in a cross section, this is what we have going on here. Underneath the material, I've got humidity, it's very controlled. On top of the material, I've got a very dry gas. Any water vapor now is permeating through or transmitting through this material, gets picked up by that nitrogen carrier gas stream, brought to this detector, and it's quantified. The cartridge itself works out really, really well. The clamp system goes inside this drawer type system on the instrument. You hit a button, it goes in, and you put some controls in place to control the temperature and the humidity, and the instrument just does the testing for you. It's really very simplified. When we look at a film test, some considerations is it's a relatively large area. This defining area is 50 centimeters squared area, which is roughly like the footprint of a coffee mug. And we use terms like milligrams per meter squared day. So we're normalizing the flux through this film to some area over time. What's interesting though about encapsulations is they're not really films. What they are is we're using it to join other pieces of material together. So here's an example of like an O-ring or a gasket or an encapsulation. It could be an adhesive that's laid down with one, between two pieces of something that's impermeable. In this case, it's glass. It could be metal, or it could be a very high barrier material. And when you sandwich these things in place, you squeeze down on them in the real life use. You're not so much worried about what comes through this glass or this impermeable side. You want to know what comes in through the edges. And that's what's really interesting about encapsulations is they're not normal like a typical film. I'm looking at what's coming through the edges. And when you look at that, well, I'm not coming through like this film face here or what we'd have there. I'm coming through this edge, and it gives us a very small, actually, cross-sectional area. So having a small area that I'm permeating through is going to lead to a lower water vapor transmission rate. Also now it's going through this long seal path. So that gave us more width. And I already said earlier that the thicker the sample, the more width there is to it, the lower the transmission rate. So that gives us it gives us a lower transmission rate, but also when let's say you double material's thickness, The time to equilibrium is 4 times longer. So if a relatively long diffusion path gives us really long test durations. So it's something that needs to be considered when testing encapsulation. Also, there might be some issues of like uniformity. How well did I put the sealant down? Is it really a uniform thickness throughout? Is my is my width good? Is my thickness uniform? All that neat stuff. So if I can't put it down in a uniform manner, taking the data in place and trying to understand how to work with it could be kind of challenging. Plus, you also add that maybe the water vapor isn't just going through it. Maybe it's kind of going around it. That kind of interstitial space between this glass and the sealant layer, or the metal and the sealant layer. Think of like a wine bottle with a cork in it. Is the oxygen permeating through the cork, or is it kind of permeating through that space between the bottle wall, the glass bottle wall, and the cork itself? And the answer is both to some degrees. Mostly through the cork, but there's a little bit, going kind of around it. So because of that, when you look at the results of water coming through it, a film, we could say nice milligrams per meter squared day. It's hard to actually estimate, what do I put in for my area of exposure? How do I normalize for this path length? So a lot of times when we look at encapsulations, we assemble them in a way that's repeatable, so we can put different adhesives in here, and then we can kind of compare just the overall flux or the overall water vapor through. So we say more like milligrams per package day or milligrams per day through this system. So that's different than a film test. And it's something to really consider when you're running a test. So someone asked, well, geez, how would I actually mount or create a sample like that? And that's where we've got clients that are really creative when they create the samples, because we're a test laboratory, but we're not the makers of the encapsulation or the sealant systems. That's not our forte. So what we'd have to do is work with a customer that could create a panel like this that has a hole in it, and another panel that doesn't, and seal them together. And if you look at this, when it's all encapsulated, it's all put together to try to look at what the permeation through the sealant is, it looks like this. This is now mounted in our cell head or our cartridge head, and with water vapor now challenging underneath, dry nitrogen challenging the top, you can now see the only way for water to get through isn't through this glass, it's not through this glass, but to come through the edge, through this area here, diffuse through this width of the panel, and then come out to the other side. So this is a great test to really understand how well this encapsulation works for the bulk properties of what's permeating through it, but also how well does it seal? Are there any edge or leakage or things going on? It's causing more water vapor to come through, at this area where they all seal and connect to each other. So the challenge with this is really that, we're going to have very low water vapor transmission rates that we're trying to analyze. We've got a long diffusion path, long test durations from it. Typical test temperatures, on an instrument, if you could fit this into a cell, we could control from 5 to 50 C very well. We can run that test. 10 to 40 if we want to use like 90% RH. But normally with these sealant tests, if you use 100% RH, it's much more precise, it's much more repeatable because you provide 100% humidity by having a wet sponge. Here we generate humidity, and you've got a little bit more plus or minus tolerances with RH probes and the like. A little bit more on the next slide when we talk about this. But what I want to get across is really with the low transmission rates for encapsulations and the setup, the strategy for this oftentimes is to try to use higher temperatures with very high humidity so we can measure that water vapor coming through. So if I mention a high temperature and high humidity, how do we do that? So we mimic the same setup, but instead of using a cartridge to mount my sample in, we use something called a remote diffusion cell. And here's a photo right here in the middle of the screen of our stainless steel cell. I can put water underneath it in this little petri dish. The sample now gets mounted on top of it. We clamp this other piece in place. It clamps in place, which allows us to flow our dry nitrogen again on the top side of the sample. And the water underneath here provides 100% humidity that then challenges our encapsulation material, our adhesive, and it makes a really great test. With this remote cell, I can now analyze it at much higher temperatures. I can put it in an oven, and I can increase it up to 85 C. I can run this test very well. Someone may ask, well, geez, if I have water in here and I'm increasing the temperature, aren't I pressurizing it underneath? I mean, that's what happens when you have water and you heat it, you're going to create some pressure. Well, the cell that we have here actually has these little coils, these little lines that allows it to the pressure to vent. So we're not pressurizing the sample. We're not going to stress the sample, crack the sample. The system is going to still be at an equilibrium atmospheric pressure, but it allows it to vent, so I can still challenge 100% RH underneath. And with liquid water in here, it's not going to go anywhere overnight. It's going to last for a good long hundreds of hours of testing, which works out really nice. I do get asked by people like, couldn't you do 85C with 85% RH instead of 100% RH? The answer is yes, you can. To do that, we have another remote diffusion cell. Here's a photo of it here. But the bottom of it doesn't have a place for a petri dish. It's drilled out. So it has a hole going all the way through it. So the purpose of this is we would still seal that sample, that prep sample inside the cell here, but we now place it in a chamber that generates 85% RH at 85C. So the chamber is providing it. It's going to challenge underneath the film because there's a hole in this thing, so it challenges with the chamber's temp and humidity, while the top is still swept with our dry carrier gas sweeping the top of the material. To attach these lines, or to attach the cell to our instrument, we have something called the remote testing cartridge adapter. So this goes in the same place that like a typical cell cartridge would on that instrument I showed you. But it goes in place and allows us to take our nitrogen carrier gas lines with tubing, come out of here, go across the cell, come back through, and then come back in this other place here with the tubing. So our dry gas is still coming out of the instrument, but the environmental controls are coming remotely. That's why it's called a remote diffusion cell. I do get asked still like 85C, 85% RH. In our laboratory, we only test with 100% RH. We don't have an 85 chamber. And anecdotally, I've been told with customers that have them that they love them because they read the readout of them, says 85. I love my testing. Until they get their second one. It's very, very difficult to calibrate 85% RH at 85C. I rented a chamber here once for a client where they wanted it done. They had to have the test. Brought in someone. They said, we really can't calibrate it at that condition. We calibrate the humidity probe at a lower temperature, and then it's assumed it's all working right. And anecdotally, I think when they get one and they get their second one, especially if they're doing other tests like maybe a calcium test or other tests for barrier, and they realize the two chambers don't produce the exact same results, then they realize, guess what? There is some variance of that condition. Whereas if you're always testing at 85C with 100% RH, that's very repeatable because temp probes are very, very good. I can get them calibrated, and they work very well. And 100% RH comes from liquid water underneath the sample. So as long as I've got even a couple drops of water in that petri dish, I'm still generating 100% RH underneath that sample. So if you look at, looking at a high temperature, high humidity application, this is a really great way to do that. Another way to look at encapsulations would be let's create a sample, something bigger than that 4x4 inch square I was talking about. So this is a real panel that was set up. It's two pieces of glass with a spacer in the middle. And they drilled holes in it at two places for us to put lines in, carrier gas lines. So now the nitrogen that comes out of the instrument, it's going to flow through this tube, flow inside the sample, come out the other side, and come in here. We put this whole piece into an environment, high temp, high humidity environment. And now we can measure how water vapor is permeating in through maybe a real life seal, if this seal is more real to your application, maybe a real part or a real component. So you're going to get maybe the variance of when you put this down, thinner spots versus thicker spots. Or how good is that interstitial space between the glass and the adhesive and the like. So this is a way to look at things. What's nice about it, with a larger edge, you can get more permeation. You get more transmission rate because there's more area to permeate through. So that's nice. It gives you higher water vapor transmission rates because of the long perimeter. The carrier gas line does have to be incorporated in. Here we use an epoxy, but if you don't want to use epoxy, you can't use epoxy, or you may doubt, geez, could I be permeating in through these little epoxy joints? Maybe use metal instead. Maybe have brass or steel or something, and weld or braze in this line. So that way you've got a great seal that you're not not worried about, but have maybe glass on the other side. That way you can still visually see how your sealant looks and make sure that there's no gapping or any problems or with this adhesive that you have inside there. So that's a good way to do it. And then you'd put this whole piece in a controlled temperature and humidity environment. Again, if you only have an oven or a temp chamber, you could put a bag around this with a bunch of wet sponges to generate 100% RH that would then challenge through here. So that's a neat way to do a test, is to mount that encapsulation as a panel and test that as a package, and then still quantify in terms of grams per day or milligrams per day of what's coming in through this quote-unquote system. Trying to normalize it again to the exposure area would still be very challenging. I think you can theoretically do it, but in this example you can see, given thin spots and thick spots, it may not be best to do it that way. It's kind of like looking at what it is per this sample, and if you have a variety of sealants or gases to look at, mount them all the same way, create the same types of packages. Something I want to point out, this is pretty interesting. I think it's pretty interesting. It's fairly new. Is something going on in Europe? Swiss technology. There's a patent out there. I think it's pretty neat. Looking at encapsulations in a way. I believe it's a very novel approach, is why I'm including it here. So Matthias Schellenberg and Christian Luppen are on the patents for this. So there's a patent out there. You can look into it. What they're trying to study initially was looking at like blister cavities, things that you've got foil to foil that are sealed together. So they should be really great barriers because you've got the foil and the foil on both sides. However, the question is, could water vapor be permeating in through my sealant layer? And try to understand what that edge permeation and edge diffusion is. I think this is really kind of brilliant. What they came up with, if you look in the patent, is a way to mask the sample. What they have is they have two masks. So imagine I've got, these are from the patent, two faces of foil. One has cutouts, these yellow areas, on one side. So if I put my material in between here, I'll see this when I look at it. I'll see a cutout here, and I'll see the material. On the other mask that's sandwiching this together is where these dotted lines are. So unlike other masks that are used a lot of times for permeation, where you have holes in them and you match them up, so they overlap each other. Here now they're offset, with the idea being that if I come through this hole here, where that yellow area, the cutout is in the mask, I'll then permeate under the mask and come out over on this hole here, which is more of the dotted line. So I'm coming from water on this face, going through the material and coming out this face on the other side. Likewise over here on the yellow, I'm permeating into the material, coming out this face, but also equally I can come out on this face too. So with that, I think it's really cool technology, because what's going on is you are definitely capturing water vapor movement through the material versus just going straight through. And this is what I think is the novel approach. And I think it's really good, practically speaking, let's say for testing or ranking materials. What allows things to go through faster than others? Which material is higher, which ones are lower. But if you try to use these in typical transmission rate levels, like grams per meter square day, or for barrier stuff, milligrams per meter square day, the surface area, yeah, okay, I can define it here, what my exposure area is, but because it's moving through in this way, it may not really be the best way to look at it, is trying to normalize to the surface area, but really look at it milligrams per day coming through, or what we say package day. And if you're always mounting the materials the same, using the same masking with these open holes on this side and then the offset mask on the other, you can now rank materials very well. You can kind of look at how good they are. So I thought this is really, really neat, novel piece. If you have more interested in this, you can contact Matthias on this directly. Yeah, I think it's pretty cool. So to summarize, when you look at encapsulation materials, they have more challenges than just a film test. They have a very small cross-sectional area, which leads to low water vapor transmission rates. They have a relatively long path length, which leads to low water vapor transmission rates and also long test durations. A strategy used to try to understand the mechanism of water vapor through them is to use, let's say, high temperatures, which increase the measured value. And as I showed with that graph of 85, then 50, then 23, it also kind of can reduce the test duration, can make a faster test as those molecules are moving faster. That's a strategy that's often employed. You can look at materials as a standard film and just look at it the standard, you measure it that standard way. Or maybe you make these specially prepared masked materials, or like the panel that I had where you're looking at the edge through the adhesive around that through that little mock-up of a solar panel or electronics panel, because that may better simulate the actual diffusion path and the like. So you have to really think about that. How am I ranking the materials, but also how are they being utilized, and how to really understand that encapsulation, what's coming through it. A core piece of this is really the equipment needs to have very high sensitivity water vapor instrument. MOCON's Aquatran 3 with our P205 sensor is like the industry leader. And also the use of remote diffusion cells and chambers, if you're doing the high temperature testing, are commonly utilized as strategies to get numbers through these materials. So with that, I'd like to thank you. And if you have any questions, feel free to reach out to me, joel.fisher@amatech.com. And I'd be definitely happy to relay, any information I can to you, get you hooked up to the right people if you're interested in the testing or interested in the instrumentation, or just overall, thoughts on this. Feel free to reach out to me. I'll be definitely able to help you out.